Welcome back, everybody. Time for one more video for today. And then it's party town. So here we go. So we have talked about one-dimensional kinematics. We reviewed how to make motion diagrams and interpret these dot diagrams. We've talked about equations, the one-dimensional equations, and how to set up a data table and how to use them even if there are no numbers. And we've also talked about graphs and reviewed how the position, velocity, and acceleration graphs all relate. So now that we have all this information locked up in our brains, it's time to put it to good use by reviewing a final review with a bunch of questions. So let's get after it. Here we go. Here are our first three questions. I want you to pause the screen. I want you to take a look at each one. I want you to put down and predict what your answer is, and then we will work them out. All right, now that we have had a chance to take a look at them, let's work them out on the screen. In this particular one, this is always look at the axis. This is time, this is velocity. So it's a velocity time graph. That means slope equals acceleration. That means area equals how far we've traveled. It says, which of the following statements is true about the motion of this object? It says the object is not moving at time equals 4 seconds to 10 seconds. Okay, so 1, 2, 3, 4. Oh, wait a minute. Let's make sure. These are 2, 4, 6, 8. So 4 to 10 seconds is from here to here. Let me highlight that right up here. Okay, that is definitely moving because on a velocity time graph we'll read across. It's actually moving at 10 meters per second. Okay, so that can't be correct. All right, the object's initial and final position are the same. Okay, position. Well, position is going from initial to final. That means its displacement would have to be 0. Okay, so that means the total area would have to equal 0. Now, these are funky shapes, trapezoids, so it's a little bit harder to do the area. But what we can do is do a little trick here. Do you see this little triangle right here? And you see this triangular space right here. They're the same. So if I just look at this area right here, this rectangle, that's going to be the same area as that trapezoid. And that area will be 10 times 10 or 100 meters. And then you can do the same thing down here. This little triangle here fits in this space. And so it's this triangular area here for the area, because this area here equals this area here. And okay, it's 5, and this is, remember, counting by 2s, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So it's 20 by 5. So hey, that's the same thing. That's 100 meters, except it's on the negative side, so it's negative 100 meters. So this is indeed correct. That's the correct answer. Let's just take a look at this. The object is slowing down from 14 to 16 seconds. 14 to 16 is right here. Let me highlight that area. 14 to 16 is right there. Now, it is indeed getting more negative, but notice it's going from 0 to something not 0. So it is not slowing down. It is actually speeding up in the negative direction. So that's a distractor. That's a pretty common one where students get tricked. And then the last one is the average acceleration of the object from 0 to 4 seconds is different than from 34 to 36. Okay, so where are those at? 0 to 4 seconds is right here, and 34 to 36 is here. So that's a rise of 5 over 1 mark over, or 2, 5 over 2, and this is a 5 over 2, or 10 over 4. So those are the same slope. So same acceleration, which equals 5 over 2 meters per second squared. All right, so our answer was B. Okay, our next one. You've got a kitten that is falling, and it's in a basket. It's kicking and rolling around because it's terrified, and the question is air resistance is negligible, What is the acceleration of the kitten basket system? Kitten basket system. Okay, so whatever this kitten is doing, this is a horrible kitten. All right, in this basket. Okay, there is a center of mass of this system. Okay, and the thing is in free fall. Since the thing is in free fall, that means only the force of gravity, which means the acceleration will equal g downward. So the only possible answer is B, that the acceleration is downward with a magnitude equal to g, because the system is a projectile, meaning that projectile means it's in free fall, only the force of gravity is acting on it. All right, and that's it. Now that's for the system. The center of mass of the system is following that. The cat and the basket may be looping and flipping around as it falls, but overall, for the system as a whole, it's all accelerating down at a rate of g. Okay. Our next one. In an experiment, 2 baseballs are dropped from the top of a tall building. One of them starts, and the timer is started, and then 1 second later, a second one. So let me draw a dot diagram for this. So here's our baseball at time equals 0, and then here it is at 1 second, and then falling farther at 2 seconds, and then falling even farther at 3 seconds. Okay? And then our other one starts here at time equals 1 second, and then it's here, it's following, it's going to fall the same, except it's a second behind. So this is 2 seconds, then here it is 3 seconds. Okay? Now, so when this one is here, this one is here. And when this one is here, this one is here. And when this one is here, this one is here. Okay? So the question is the difference in the velocity between the 2 balls decreases as they fall? Well, difference in velocity. This one's velocity after 1 second will be 10 meters per second. And then here it will be 20 meters per second. And here it will be 30 meters per second. Let me move that up a little bit for you if I can. Okay, because it starts at rest. This one's the same way, except it's just going to be 1 second behind. So when this one is here, this one's here, this one's at 0, that one's at 10. So that means the delta velocity between the two is going to be 10 meters per second, or 9.8 meters per second. I'm just using 10 because it's easier. And then here, this one's going 20, but this one will be going 10. So the difference is, again, 10 meters per second. And when this one's gone 3 seconds, this one's gone 3 seconds, but 1 second behind. So this one's at 30 and this one's at 20. So again, the difference is 10 meters per second because it's just following it 1 second behind. So the difference in velocity is not decreasing, it's remaining the same. So the answer is B. You can also see that the distance between the objects is going to be getting farther and farther and farther apart. They're this far apart at first, then they're this far apart, and then they are this far apart. So they're getting farther and farther and farther away. So all those superhero movies where, say, like, who was it? Gwen Stacy falls off a building and Spider-Man jumps after her. Spider-Man never catches up. Gwen Stacy is always getting farther and farther or farther away from him, unless he starts with an initial velocity. So like he uses his webs to go start with an initial velocity to catch up. Then it's possible. All right. So those are our 3 multiple choice questions. So now let's do a free response question. So take a look at this. Pause the video and try to work this out. There is a second part to this. I added this on. Would you also plot an XT and an AT graph, or at least sketch it and then set up an XVA data table for both the truck and the car so we can get used to using this symbols with our equations. All right, now that we're done, or you're done, let's take a look at the problem. So I'm actually going to do this last part first, I think. So let's set up the data table. So here's X naught, X, V naught, V, A, and T for the truck and the car. So the truck starts at 0, and so does the car. They both end at D. The truck starts with a velocity, V truck. The car starts with a 0 velocity. The truck ends with the same velocity, same, because its acceleration is 0. And it says that it ends at a time of TD when it gets there. And the car is also going to get there at the same time, TD. But its final velocity will be something else. It has to be faster than the truck, right? Because otherwise it'll never catch up. And then the car will have to accelerate, of which we don't know that either. All right? So there's our data table in symbol form. So now let's go up here and do our graphs. So our truck starts here at some velocity. It says to make sure you label it. So here's T for truck. If you don't label it, you won't get full credit on the test because they won't know which one is which. All right, so please make sure that you actually label it. And then the truck goes at constant velocity, so that's easy. And I'm going to end it right here just because I can. I'm going to call that TD, the time it gets there. And you should stop the data there. They're looking for this. So they graph it up to that point. All right. And then the car starts down here. I'm going to label that as C. And then the car is going to have to end up at a higher velocity. Now, if I do this right, let me get a straight edge here. It's going to have a constant acceleration. All right, and there you go. So if you can't draw a straight line on the test, just write down straight line, just so they know, in case you like draw something wonky and you're having trouble because you're nervous. Just write straight line, and write constant velocity over here if you want. If you notice, this one is going twice as fast as the truck is. So if this is VT here, this has to be twice VT. Okay? And that ought to kind of make sense because remember, they both have a displacement of D, the same. So that means they both have to have the same area. So if this area here, this triangular area has to be the same area. So the only way for that to happen, if you remember your geometry, because the area is 1/2 base times height, is for the height to be twice as big. So the final velocity has to be twice so that we get the same overall area. Okay. It's important to put all that detail in. It helps you out tremendously in the rest of the problem. Okay, what will the xt and the at graphs look like? The position time and the acceleration time. Let's start with the easy one, which is acceleration versus time. First, let's talk about, real quickly, what the different motions are like. The truck is constant velocity. Therefore, its acceleration is 0. And the car is constant acceleration. Okay? So we should know what those look like, and these should be relatively easy to draw. So I've already started the truck here. The truck has a 0 acceleration, so its acceleration is down here. The car has a constant positive acceleration. We can see that in our graph because in our graph we have a positive slope, okay, on our velocity time graph. So we should be up here somewhere for our car. And then the position versus time, let's do the easy one again first, the truck. What does constant velocity look like for the truck? Well, constant velocity would mean a constant slope here. And if I have this as my starting spot, it should look like this. This should be the truck. And then the car will look a little different because the car has a constant acceleration, positive, which means we should have a curve upward. Car starts with an initial velocity of 0, and then it ends with a large velocity over here, but they end up at the same place, D, at the same time. So I should have a parabola going up like this. And that's how they should meet. I actually have a simulation of that so we can take a look at it. It's right here. So the blue one here is going to be the truck. Starts at 0 position. It has an initial velocity of 20 and it has no acceleration. The car also starts at 0. The red car starts at 0. The red car starts with a velocity of 0, but it has an acceleration. I just put in 5. If we hit run, we'll see that the blue one gets ahead, but the red one starts to catch up as it goes faster, and they meet right here. And that's exactly what we drew. Outstanding. So somewhere in here, about 4 seconds, it should be exactly at 4 seconds, they have the exact same velocity, same slope here as here. And then the car is going faster over here. And this is a position time graph. All right. So now let us take a look at our next problem, or the next part of the problem. And here it is. If you'll pause the video, see if you can answer this, and then we will work through it together. Okay, so let's take a look at this one. Now, this is one of these, what's sometimes called as a student contention or conflicting contention response or problem, where somebody says something else, they're not the same, and your job is to determine what's correct, what's incorrect. Now, please be careful. Please be careful. Answer the question. All right? So here are the two student statements up here. But it says, which aspects of students' reasoning, if any, are correct? So answer the question. We don't care what they said is wrong. We only care what's correct. And then it also says, support your answer in terms of relevant features from the graph. This is where a lot of my students have trouble, is what they do is they correctly pick the correct part of their statement, but what they forget to do is to answer it the way it's been asked. They want you to use the graph from earlier to make your answer or make your argument, okay? So let's take a look at student 1. The distance traveled by the car and the truck is the same. Well, that's true. Okay, so that's good. And the time is the same. All right. They travel the same distance in the same time. They must have the same speed. Wait a minute, we know that can't be true, because when we look back here, we see that the truck has a constant speed and the car has an increasing speed. So there's only one spot right here where they have the exact same speed or velocity. So that second part of the statement cannot be correct. So this part is correct. So we put that down here. I always encourage you to box in what's correct, cross out what's wrong, and move forward. Now, how can I support this with features from the graph? Well, I only care what's correct. And it says they traveled the same distance in the same time. But here's my graph. How can I tell distance on here? Well, remember, that's the area. So that's this shaded stuff. So the shaded area for the truck has to equal the shaded area for the car, and that's why we know this final velocity has to be twice as large as this one, so that the geometry works out, so they're the same exact area. Okay? So we would say that they travel the same distance in the same amount of time, and because the area of both graphs is the same. Done. Okay, so for the second one, it asks essentially the same question. What parts of student 2 reasoning is correct? And support with terms or something from your graph. Okay, so we're only looking at what's correct again. So let's take a look at theirs. Theirs says, I don't see how that can be. The car catches up with the truck, so the car has to be going faster. Okay, the car does have to be going faster, so we know that's correct. So, car is going faster. We put that statement down here. And then, how can we prove that from the graph? How can we prove that in this graph that the car is going faster? Well, it's because it's higher up that the car's graph is above the truck's graph. So you just say at time equals TD, car's graph higher than truck graph. Or it's above the truck's graph. All right? Piece of cake. So now let's look at the bottom part. Part C, derive an expression for the acceleration of the car. We've kind of done that. We've set up our table right here already. So if we look at our table right here, we can see that we could find the acceleration of the car. Hey, we do need to know what this final velocity is. We've already decided that it's twice. So that's 2vt. All right, so I could find the acceleration, and that equals delta x over delta t. So the delta x would be, I've traveled distance d over t sub d, and we're done, right? Oh, unfortunately not, because it's always important to answer the question that they asked. The question is, derive an expression for acceleration in terms of d and vt. So no time. So back to the drawing board. So right here again, we have this information, but we cannot use the time. All right, so if we can't use the time, well, that lends us to this equation. V squared equals V naught squared plus 2a x minus x naught as our equation. And we can see that if we plug in where our zeros are, that's 0, and the initial velocity is 0. So our final velocity has to be twice vt squared equals 2a, and that's d. Now solve for a. A equals, let's see, that's 4 vt squared, because I squared the 2, divided by 2d, so that means it's 2 vt squared over d, and that is our answer. And now we've answered it the way they wanted us to. This receives full credit. This other answer, which is correct, by the way, would not receive credit because we didn't answer the question they asked. Does that make sense? Just make sure you use the symbols they asked for. And then our last question is, determine the time at which the speed of the car and the speed of the truck are the same. And we've actually already answered that earlier because we drew a great graph. And that is, look, this is a triangle, that's a rectangle. This has to cross here at half the time. So this spot right here would be TD divided by 2. So the question says determine, and it says express your answers in terms of TD. And so we would and it says justify your answers. So our time would be, TD divided by 2, and our justification is that's where the graphs intersect. Intersection of graphs in part A. Done. Next question. It's a weird question. Read it. Try to answer it. Pause the video. Okay, so let's take a look at this one. Now, in this particular one, we have a very long track. This is only showing you the section of the track that is where it's got a constant velocity, constant average velocity, all right? So let's just take a look at this and see what the heck's going on. As this thing moves down, do you see that it's going to accelerate, say like a positive acceleration between here and here? And then at this bump, it's going to have a negative acceleration. It's going to slow down. And then it's going to accelerate here again. Then it's going to have a negative acceleration, and so forth. So what would that look like on a velocity time graph? Okay, because that's what we're having to graph. So a constant acceleration would be an upward slope. And it says that we have a constant velocity, the section where we're beyond, where we have reached an average velocity. Okay? So we're going to have an average velocity through here. Let me draw that in a different color. So our average velocity will be here, V average. Notice I tried to draw it horizontal, even though my drawing's kind of crappy. And then this is going to jump down because it's going to slow down in a very short period of time on these with these bumps. And then it's going to speed up again, and it's going to slow down, and it's going to speed up again, and it's going to slow down, and so forth and so on. So it's going to look something like this. When they graded this, they wanted to see something linear in here, in between the bumps. They wanted to see some sort of reset where it moves back down. So it didn't have to be perfect. Something linear, and then some students drew something like this. Some students drew something like this. But the thing was is that it was, and some students drew something actually curvy. The thing was is that there was a short reset and then a linear section in between. All right? That's what they were looking for. And the fact that the average stayed constant. Okay, now, suppose the distance between the bumps is increased, but everything else stays the same. Will the maximum speed now be greater than, less than, or the same? All right, well, if we increase this distance in between, we'll have more acceleration distance before we have to slow down. So we should be getting faster. So the answer is it's going to be greater than. And so some justification that there's more time or more distance to accelerate. There's also kind of a cool way to answer this as well. Some students answered this as they said, well, now there's more gravitational potential energy converted into kinetic energy before it slows down. So the average velocity will be greater. That's actually a really cool way to explain it as well. All right, so the next part of our question is with the bumps return to the original spacing, the track is tilted to a greater angle theta. Is the maximum speed greater than, less than, or the same? All right, so think about it. If we have something on a track like this, or we have something on a track like this, we're going to have much more of our gravitational force down the incline. You can see that this portion of the gravitational force gets bigger. The Fg sine theta portion, where this is our sine, that's our theta right there. So we're going to have a greater acceleration. So something, it's going to be greater again. So something to the effect that you have a greater gravity force or gravity component down the incline. So you have a greater acceleration. Okay? And therefore, since we have a greater acceleration, so greater gravity component down the incline, therefore greater acceleration, therefore larger average velocity. Okay? So now let's do the last part of our question. Okay, so here is a odd question. But now that we have done some of these proportionalities already, and the factor of change questions, we've also worked them that way. We ought to be able to work this problem relatively easily, I hope. So take a look at this one, pause the video, work it out, and then I'll help you. Okay, so if we look at the question, we have this equation that the student has come up with to try and predict what's going to happen. And then they did an experiment where, this is important, they changed the mass and they measured the average velocity. Okay? So these are our two variables. Independent variable, dependent variable. And it says, are these data consistent with the student's equation? So what they're asking is this stuff right here consistent with this? Okay, well, this equation has a bunch of variables in it, but we're only interested in m and v. So let's break this down into v average is proportional to, forget about everything else, where's the m at? The m's in the numerator. So that the student has predicted that they'll be directly proportional. So look, if this goes up, that goes up. Is that true? Well, yes. But if this doubles, does that double? And the answer is, well, no. If we go here and go across, we get about 1.5. And if we double the mass, go here and go across, we get 2. So it does not double. This actually has an intercept of around 1. And this doesn't show that there should be an intercept. Should go through 0, 0. They're predicting it's directly proportional. So the answer is no. The graph does not go through 0. Their equation predicts this. Okay? Their equation would be better if they'd have done something like this. V average, and then they have maybe CMG sine theta over D, like they had before, but there should be an intercept plus some other constant. Call it constant number 2 if you want. Okay? They're missing that from math class. All right, last part. Another student suggests that whether or not the data is consistent with the equation could be incorrect for other reasons. Does the equation make physical sense? All right, so let's take a look. This equation predicts that V average is directly proportional to G. So as G goes up, V goes up. All right, well, that seems to make sense. If gravity was great, if we did this experiment on Mars, it should be less gravity, it should roll down slower. If we did it on Jupiter, more gravity, pulling it down, it should accelerate down faster. So that seems to make sense. So happy face there. How about V average is proportional to, this is in the numerator, sine theta? This one's a little harder. So let's take a look at the sine equation, what the graph looks like anyway. So sine of theta and theta. So if you remember from math class, this is a sine wave, right? But this ramp will start at a 0-degree angle, and as it goes up, it'll pass through something like 45 degrees, and then the maximum it'll get to is 90 degrees vertical. Okay, so that part of a sine wave goes like this, but from 0 to 90, that's 0 and that's 90, it's going to go like this. So as theta goes up, sine of theta goes up. So as theta goes up, this side goes up, and the velocity in this equation should go up. Does that make sense? As we make this steeper and steeper and steeper, does the average velocity go up? Well, that was our argument on the first part of this problem, right? That as it got, here it is, right here on the front page, that as it got steeper, it should go faster. That makes sense. Okay, so we got another smiley face there. That looks good. So the only other variable we have left is D. So V average is proportional to 1 over D. So what this says is that as the distance goes up between the bumps, the velocity should go down. Well, that's a problem because that's a direct contradiction to what we said on the front side. As the distance gets bigger, there's more distance and time to accelerate, so it should be faster. So that's a problem. So we say that it does not make physical sense. And then our reasoning is that D is inversely proportional, sorry, I'm talking and writing at the same time, to V average. Should be directly, well, I don't even know. You know what? I don't know what that should be. Maybe it should be directly, maybe it should be directly squared. I don't know. So I'm just going to say that it's wrong because it's directly proportional. And I'm going to say as D goes up, V average should go up too. And there you go. Smiley face. And we're all done. Hey, this was a long video. I appreciate you all hanging with me on this one. That's it. It's Friday. It's the end of the day. It's the last video. So, party town. Everybody have a great weekend.